just as a means of introduction, at ATTO Technology, I'm the software technical lead for a line of storage controllers. We have protocol converters, fiber channel to SAS SATA. They can have RAID or not have RAID. We've done iSCSI. We've done, our front ends and back ends they move along with the technology. And one of the things that we're very interested in is optimizing the flow through our protocol controllers, so through our marketing people call them extremes. I don't know what the heck that means, but through our controllers, we're very interested in optimizing the path through that and getting that as quick as possible. And so one of the things that everybody always does, right? They always just run the benchmarks, okay? You got your AJA, from IOMETER is there. They just run all the benchmarks. But the problem is that benchmarks kind of lie. Now, kind of. They're giving you these aggregates, right? And that's the real problem that we started running into. So what are we looking at? Yeah, they'll give you a minimum and a maximum and an average. IOPS or megabytes a second, or you can get latency out of them. But the problem is you're getting all of these aggregates together, and you don't really have a good idea what's going on, especially if you're in something like a bimodal system. Something that's fast at some time, slow at others. Well, you're just going to get a straight line that's kind of your average in the middle, and you don't really realize what's going on with that. When we start to get into multi-initiator situations, which you do, in a SAN very often, we get the same thing because we're averaging from server to server to server, and it skews our numbers further. So it becomes a problem. When we turn on our RAID stack, we even have bigger problems because the cache decisions that the RAID stack is running, it creates noise. Now, I had some of my team where they were a little bit, they didn't really like the word noise. They liked complexity better. It's not noise, it's complex. But if you're doing an analysis, it looks like noise to me. I mean, it's very difficult when you have direct reads and early statuses and things like that. Or if you're rebuilding, if you're rebuilding, you can end up having smaller IOs and they're stuck behind the large ones because the drive's prioritizing the IOs for the rebuild or something along those lines, or maybe our controller's doing it. And as soon as you get a noisy system, it's harder to analyze, okay? Because the averages are going to hide those smaller signals, okay? And those smaller signals are often the key to what's slowing you down. So one of the things that we've been very focused on is measuring latency alongside IOPS. A lot of times, again, the benchmarkers are going to give you IOPS in megabytes, and we're like, no. Let's look at the latency. So in FIO, for example, you can get the bar graph that comes out. In XPerf, you can get a line that's giving you the latency, the overall latency, okay? And these things are going to give you that visibility that you need because you can spot bimodal systems and you can weed out those hiccups. Those hiccups are the things that you're really trying to look for. So if you've been doing SCSI as long as I have, you have, like, every time you see a drive break, you set it aside and you right? SW knows. So I have this JBOD of broken drives that I like to slap stuff into and just see how awful can awful be. And so I put together just a quick IOMETER test with some drives that are just really misbehaving themselves. And okay, so I had 6 spinners, all right, 4K random reads, all right, and I'm getting like 15K IOPS out of it, which, boy, that's wonderful. So then I did a scatter plot of the thing, okay? And that looks kind of like a Seurat painting, doesn't it? The pointillism. You can't really tell what's going on there, okay? And oh no, did I load the wrong slide deck? Hold on. I might have to load something else. Oh, no, I did not. I'm sorry. I had a couple different versions of this. I apologize. So what you're looking at here is each one of these drives, you can see a legend on the opposite side. You know, I've just got like stuff going all over the place. So you would expect if I'm getting 15K IOPS that I would see a nice band if everybody's right in the middle. But you can see there's stuff going on like that's really, really nasty here. Okay? And like I said, it's very complicated. So what we ended up doing is there are these guys, Brian Cantrell and Brendan Gregg, and they were working at Sun Microsystems on ZFS, and they put together a way of visualizing some of this stuff called a heat map. And we were very interested in that. I actually, there was something in the communications of the ACM that I saw it, and I passed it on to one of our guys. But what it's doing is it'll do time compression, but you're still getting slices. All right, so it's not just a big average. You get slices, and the colors will show a recurrence of the same the same number within a sample period. Okay, so you have your X and Y, but the color intensity is the third dimension. And if you're interested in this stuff, I'd really get this slide deck and go to Brendan Gregg's. Yeah.
These are the same guys who did the "Don't shout at your hard drive."
Yes, they are. Yeah. And then you saw it moving. Yeah, those are the. Yeah, that's those guys. Go to his website because I mean it's all in Python, and you can pull this stuff into your anything that you have that's visualizing. It's really good, and I'll show you because let me pull it back up to this point-to-list painting here. That's really messy, and it's difficult for us to see any patterns in that. But when I go to a heat map, suddenly I see something really neat. Now I got a big bunch of latencies down in this region here. Now, full disclosure, it starts at 4 because I wanted to fit it on the slide. So it doesn't start at 0, just so you know. There's a bunch here, but look, you have something going on in the middle there, right around 7.5 milliseconds that, boy, there's really... Now, the depth of the color, again, tells you how many occurrences you had of that particular value. So that means I have a whole bunch of latencies that are coming in measured around 4.5, 5 milliseconds. Remember, they're spinners. And then around 7 and 7.5, I'm getting serious peaks. This is one of those things. It's kind of one of those bimodal systems that I was referring to. So what I've done here is I separated the drives out and I grayed out the ones that the ones of interest. So what that heat map did is it pointed me to, boy, I better look at these drives independently and see what's going on. And I see this band now that showed up in the heat map. Okay, right at around 4.5 of 5. 3 of my drives are actually doing pretty well, and they're kind of hanging out down in that area. But drive 5, boy, that thing's looking nasty. And if you see in here, it's a little harder with the colors there, I apologize. But if you can see, what you're getting is there's a tick here, on a pretty regular tick, that's getting us all the way up to 7.5 millisecond latency.
That tick is very visible, by the way. What is the tick at?
What's that?
You said there's a tick somewhere.
Yeah.
Right. Can you see it here and here and here?
It's a color blindness test, actually. if you can't see the message, it tells you where to go.
This slide is actually covered from Rorschach.
Well, I actually do have trouble discerning colors, and that's why I didn't tell you which color it was. So I can see it because I didn't make them red and green. So we're seeing this. Now, this whole thing is pointing to the fact that, look, if I start taking finer measurements of the latency, and it'll start showing me really cool pictures. All right. So I want to change gears a little bit right now. I'd like to just, probably nobody in here needs to actually get this reminder, but I'd like to just look at some basics of how a storage controller algorithm fits in here. I'll go very quickly, just so we're all on the same plane, all right, so that we all know what's being talked about. Okay, and then I want to talk about what the latency measurement system that we threw into our controller is, because it's pretty cool. And I'd like to finish with some real-world examples that we got, because the real-world examples are really where this thing shines. It's neat, okay? So just very quickly, everybody knows, you know, if you have any kind of your storage algorithm, you know, it doesn't really matter what protocol you're in. You're going to have a command phase. You're going to validate the command somehow, whether that happens in your software stack, wherever that happens. There's a data phase where there's a data transfer. In this case, this is a data in type of a command. And then the data in status, and there's a cleanup. So this is, we're familiar with this. We're storage professionals. We understand that pretty much anytime you're trying to do a transfer, these steps have to happen. Sometimes they'll get collapsed, and sometimes they won't. But this is kind of what happens. Okay? Now, in our typical storage controller, and Tom Friend, is that his name? Yesterday, he was talking about optimizing drives and stuff like that, and he was talking about how there's a fast path and a slow path. You know, typical storage controller nowadays, it's a system on a chip. So you have a protocol engine that, you know, you have a data plane separate and a control plane, all right? So your data plane is your fast path. Reads and writes are going to blast through that. They don't have to have any kind of software in the way in the controller. You just write through your data plane. That's for moving the data quick. And then you have a control plane for everything else, if you have errors or anything like that. Or other commands that aren't reads or writes or verify, that kind of thing. All right? And this is the same kind of thing that Tom was talking about inside the disk drives. He's like, oh yeah, you always have a fast path and a slow path. Okay? So inside a data plane engine, this is an example of one. Okay? Now, all of those phases that were in that previous chart are kind of represented here. If I step down, you can still hear, right?
Yeah.
Okay. So what we're doing here is we have protocol engines at either side, right? So we can do our conversion. Say, for example, this is say you got fiber channel over here and you have SATA over here. Typical example for us. Okay, so you have a protocol engine on either side. All of those steps have to happen. Okay, command has to be validated. Okay, you have to allocate buffers for it. Yeah.
If possible, if you turn it, at least face the mic, and the recording might pick up some of it.
Oh, okay.
You probably still stand down there, but you have a lab mic. Oh, you do have a lab mic. I didn't know that.
I didn't either.
Yeah. Thank you.
Is this better? Okay. All right, so is that too loud? Okay. All right, so these steps, the steps that I showed before are, they're all represented here in blocks, okay? The only difference is that you have hardware blocks that are doing it, because this is your fast path engine, okay? So you're going to still do your command validation, your routing. You're still going to have to issue a target command. You're still going to have to take your response and do your data transfer, okay? You're still going to have to respond back to the host. All of those phases are represented here, okay? Then one of the very tricky things is how your validation works, because what's going to go to the now I'm going to take this away or I'll sound like Darth Vader. So the question just becomes, what's going to go to your control plane and what's going to stay in the data plane, okay? Now, the problem that you have with this is very opaque to your software. And we were just talking about, I need to make latency measurements, and I need to measure my latency in the different pieces and everything. But now I got a piece of hardware that's doing my transfer for me. What am I going to do with this? Okay? Especially when Oh, I should mention that obviously if there's RAID here, you'd have other components in the middle. This is just doing a protocol translation. You'd have your caching and your RAID and all of that stuff pretty much right in there. And we want to accelerate this storage system, right? We have the transfer, it's split into subcomponents, but we need to make these fine-grade measurements, okay? Because one of those components is wrong, your whole thing can be out of whack, okay? And especially if it's not consistently bad. If you have a situation where once in a while, I think I'm going to act up. Well, those things do not look very nice. Overall, they're going to hit you pretty hard because your pipelining falls apart. Okay, so what do we do? I want to optimize my system. I got to iterate through. I got to identify the bottleneck. I got to mitigate it. Okay. Yeah. So what does this have to do with latency? I thought I was talking about latency. Well. Like I said before, that data plane processor, it's opaque. I can't see what's going on in there. And I need to measure because I can't optimize without measuring. Okay? The control plane processor is going to be responsible for gathering statistics because you don't want to do too much in your data plane. You want to move data around. Okay? I don't want to hurt that. So what we ended up doing is we actually put a timestamp into our data plane. Another feature that I've never seen anybody be able to get away with in any kind of storage system is there's always something to hold a command context. There's always some structure that has information, I don't know, Lun and CDB and all that stuff. So what we did, we made it very clean because we didn't want to take a lot of time. We put 2 timestamps in each one of our command contexts. Okay, now we can configure each one of those engines that I was talking about. Are you the start? Are you the end? Or are you in the middle? If you're in the middle, don't touch it. If you're the start or the end, write the one timestamp and write the other timestamp. And we also were able to put filtering in by Lun because you'll see that's very helpful. And the cleanup engine at the end, it's responsible for calculating the delta between those 2 timestamps. And instead of storing them all in a big log, the cleanup engine, it can do this quickly. It bins them. So you can say, all right, well, let me configure the bins, and maybe I want a logarithmic scale or something like that. And that way, the readout from the control plane processor doesn't have to go and sort through this whole huge thing. Because what I really want is I want to say, okay, what's between 1 and 2 microseconds here? What's between 4 and 6 microseconds here? Because those are the things that I really want to see. All right. So this is just another representation of that. Okay, and at command completion, like I said, we bin the timestamps. We ended up just putting 8 in. That was enough resolution for us. Again, by Lun. And currently ours has a 1 microsecond 20-bit resolution, but I've been discussing that because we're starting to cross that threshold where 1 microsecond is not. It's too coarse for us. All right. So what does this look like? Well, now I have these timestamp bins in my data plane engine. So there's just a new component here. When the buffer is being returned at the very end, now there's a timestamp binner, and all it does is it calculates the delta, runs through and says, okay, which bin does this go into? All right. This ends up being pretty flexible because I can say, well, what's the latency through this component right here? Or what's the latency, through these 2? I want to take the drive out of it. Can I get the latency, the latency without having the drive involved? It ends up being, like I said, very flexible for us because we can look at particular LUNs and where they are through each of our components. And again, this is a little bit simplified. Yeah, I didn't want to make a eye chart with a myriad of components in here that are available. Okay, so just real quick. So we talked about latency measurements and their importance, at least for our application. Showed you guys heat maps. I really encourage you to get that slide deck and look at his stuff. It's amazing. And we're measuring in the data plane. So I'd like to show you guys now. I'd like to just take the rest of the time. Oh, I'm early. I'd like to take the rest of the time and go through some examples and show you what you can gain when you start doing latency measurements at this kind of a scale. We had a particular customer come to us, and they were using RAID, and they were seeing, well, actually, they were seeing pretty crappy performance out of us. Now, again, this is real world stuff for ATTO technology, and our customers still use spinners. Okay, so you got to understand. I mean, we go into racks and racks with 950,000 drives and stuff like that, and a lot of them are still spinners. That's what's out there. When you're at this conference, it's kind of interesting because you hear all this stuff and you think that everybody's using SSDs, but our customers aren't all ready to pay for that just yet. So what they ended up is they were getting bad performance, and just take a look at this is a cumulative latency histogram, okay? If you just look at this, you're going, I don't really know what's going on. When I go back to the heat map, I see, wow, this is bimodal, right? I got a big line here, and I got a big line here. And my customers using, these are all the same drives, and it doesn't really matter because it's going through our RAID engine anyway. So what in the heck is going on with this? Well, I want to make sure I tell you which example is which. So what we were seeing here is that we're early statusing to get these sub 100 microsecond because it's our RAID, okay? They're doing 4K writes, and we're early statusing the writes because you're like, okay, those are in the cache, those are in the cache, those are in the cache. But what ends up happening is because of the queue depth, we ended up filling up our cache, and there was a problem in our RAID algorithm. Okay, so we have a feature that's called redirect that basically helps with your early statusing. And once we got to this queue depth, they had not configured this feature, and so we stopped early statusing because of the way our queuing algorithm was set up. So when they enabled that feature properly, we ended up being able to solve this problem for them and say, no, it's all this fast. What you saw was this line extended a little bit higher, but you didn't get that bimodal thing. Now, without being able to take those measurements and without a heat map, if I just had cumulative latency histogram, the one on the right, I probably wouldn't have seen it, This is very powerful then. We had another customer, and this is what the IOPS looked like. Now, not all the time, but they'd be going along and it would just shelf, it's just bang. And then a little while later, it would slowly recover, run for a while, bang, and hit the shelf again. And we're like, what in the world is going on with this? Okay, so this was a similar kind of a RAID. 15 drives. This is 4K random reads. 64 queue depth. Okay? And check out this heat map. Isn't that neat looking? Wow. So that's the shelf. You can see it. It's really clear. Okay? What ended up happening is one drive in the RAID group was delaying, about 1,000 milliseconds. It was waiting a second to give us our data. And it was just one of the 15. And again, this was very easily solved by us because it was a configuration issue. In most RAID stacks, you can say, hey, you know, if one drive's misbehaving, give me my data, calculate it from the parity. I mean, it's a RAID 5. I should be able to just calculate. I got it all in my cache, in my stripe cache. I can just pull it out and calculate it. And they hadn't configured it. So they're like, hey, how come this is doing this? And we said, well, you got a bad drive. And they said, yeah, but a bad drive's not supposed to be giving us that kind of performance. So we looked at their configuration and said, okay, well, this is a feature that you really have to enable. We think that they didn't know what it was, so they turned it off. Now, I have another one, and this was not a specific customer problem, but it looks so cool, I had to bring it. So this is all run in SCSI, and look, it's a Lun Reset. So here we have a RAID 5 going on here with 4K writes. And when we were measuring some of this stuff, we had a little delay at the host, and it caused a Lun Reset. But look at how neat this is. I think this is really cool. You can see what's going on here. We're going along, and once again, we have a little bit of bimodality because of our cache filling up. Okay, but it's not as bad as what we were seeing before. Big band right here. But when the Lun Reset comes, there's a big just a big aggregation of early statuses that go back, again, because the cache is flush. So the Lun Reset comes in, and what do we have to do? Well, we got to abort everything that's outstanding and essentially clean up all of our cache. So when the Lun Reset is acknowledged and the host starts kicking us again, we get a nice burst, a little star of early statuses, and then everything returns back. I just thought this looked really cool. So I wanted to share that. All right, so I have one more example, and I'm going to change the way the heat maps look because I want to show you one of the things when you separate by Lun. So I was just using IOMETER. I had 120 drives. 4K sequential reads. But what we put in place was a workload where one of our Luns, we ended up doing a 1 megabyte random read through there. So you got these two workers. Most of them are just kicking out all of the 4K sequential reads. And one of the Luns, the other worker, I should say, is hitting one of the Luns, excuse me, with 1 megabyte random reads. And it looks very interesting because the heat map has banding in it. Okay, now I put a little explosion over there. The y-axis is now Lun, so I've kind of changed the view on you. I wanted to make that clear. All right, so we have 120 drives here, and well, I guess they're not all being used, but 105 drives here being used. But look at this. You can see, again, you can see just the little tick marks on this Lun. So this is Lun 0 and Lun 105, give or take. 78 is right around here. And you can see, okay, well, that's fine. Those are my 1 meg random reads. Okay. But down here, I see this banding where all the drives are reacting. And it's like, what's going on with that? That looks pretty odd because all the drives are slowing themselves down. Okay? And, well, let's verify this through some other latency. You can see the IOPS. Look at the dip. Because all these drives are responding. Okay? So the latency distribution on the Lun in question is okay. The bandwidth is okay. But there's something weird going on. So then what I ended up doing is I said, well, let's just look at this one. Okay? Now we're seeing that the bandwidth is looking just fine. The latency distribution is looking just fine. But this is your 4K IOPS and here's the other, but you know, it's like, what's really going on? It didn't make a lot of sense. Okay? So this is Lun number 1. This is not the one that's that is getting hit with the 1 megabyte randoms, but it still has these peaks. And that's what the banding looked like. So we started measuring the different points in our controller and saying, where is this coming from? You know, looked at the drives. They all look like they're doing okay. In fact, yeah, we looked at the drives. They all looked like they were responding reasonably, all the different pieces. So we looked at just the ingress, and it turns out the commands that we're getting in, there's latency on the commands that are being sent to us. So somehow the system is responding pretty quickly, but the commands that are coming in quite a bit slower when this tick hits. All right. Well, of course, one of the testers who knows a lot more about things like this than I do said, well, duh, you've got 2 workers there. You know, you have all these drives and all this I/O and it's backing up on 1 worker. He said, you know, if you spread this out to multiple workers, yeah. So what did I do? I put 20 workers in because that was the max I had available. And suddenly my IOPS went way up. Woo! That looks good. Okay. This is the same configuration except now there's 20 workers instead of just the 2. So that we're getting backed up, queued up someplace in the stack behind IOMETER. Okay. Now Lun 1 looks good. We have a nice solid band here. We don't have those jumps. Okay. And here's a nice, interesting thing that happened. All right. Well, first of all, the band's pretty much disappeared. You still see the tick. Now here's a kind of an interesting thing, and this is tying us, we've come full circle, because benchmarks can lie to you. Because now we have much higher IOPS, but look at my average latency. My average latency is way higher. Okay. So that shows you that, you know, when you have queues and you're dealing with queuing theory and a bunch of stuff like that, your benchmarks averages can't give you the kind of information you need. Well, what turned out here is if I were to look at queue depth, I would see this. The average latency went longer because there's a much higher queue depth lined up. I'm sticking a lot more, Little's law, right? You know, so now I'm sticking a lot more I/O out. There's a lot more I/O outstanding at a time. So we got I think a third better IOPS, but an order of magnitude drop, well, gain, however you want to describe it. Our latency is an order of magnitude worse, yet we got 20 to 30% more IOPS. It's kind of cool. All right. So that's where I was. I just wanted to show you some examples of how powerful these heat maps can be and how powerful it is when you do finer grained measurements than just, let me give an average of all of my latency on a line. You know, if I can split it by Lun, if I can split it by subsystem, if I can put these little points inside my system. Now we did, by the way, we did implement this in software first, and we had good success with that too, and it cost us maybe 1% in our performance when we did it in software, because again, you're only storing a couple numbers and you're binning them, you know, instead of trying to go through a huge list and figure it all out. So, all right. So, yay, I'm early. Are there questions about what we were doing? Any questions?
So what is the takeaway from the real presentation? Can you summarize that?
Sure. That if you're trying to optimize a system, your standard benchmarks that have aggregated the information, that give you average megabytes, average latency, average IOPS, those types of things, they don't have enough granularity for you to optimize your system. And if you build something in like this, I mean, we're all developers and stuff. You could build this in your system. If you build something like this in your system, your opportunities to optimize are much better, and your opportunities to debug your customers' problems. Sorry.
What's the cost of this in engineering terms and sort of ongoing irritation, any perf effects, any maintenance or support issues?
Yeah, that's a good question. First of all, the performance, because it's in our hardware, is negligible. We do see a reduction in the performance of the control plane because it's aggregating and turning all this stuff back into us. But that's not affecting, our customers. As far as the way the system to generate the heat maps and that kind of thing, that's all Python. So as far as engineering cost, it's pretty light because, Python libraries, right? So what we do is we basically open up a socket to the target, have the control plane processor just stream the stuff to us. We aggregate it and, excuse me, that was a good lunch. We aggregate it in Python at a different host. So that's not a problem either. As far as ongoing irritation and type, the ongoing irritation is really asking for more features and that kind of thing. It's not, there's really very little maintenance on it because it's a very simple system, right? Taking a couple timestamps and binning them.
There's definitely ROI there. We've got something very similar.
Yeah.
And there's definitely ROI because we solved 1 million problems and paid for that engineering time.
Absolutely. Absolutely. Right. And as far as the changes in the FPGA, I'm a software guy.
So, if you're not getting any more questions, so Eric Brewer at Google gave a pretty well widely viewed talk on how their key metric is tail latency.
Mm-hmm.
Are you hearing that from your customers? Can you easily show that? Did you have to?
No, you know what? We haven't gotten that feedback, so I heard some of that around this week, and it's on my list of, hey, how can we look at that? But no, I don't. That's not the feedback we've gotten. So
You should go go listen to the recording and slides we talked from Fast.
from Fast
Yeah, it was not. I think it was last year, not this year.
last year. Okay. Yeah, I get the proceedings, but they're always this thick, and I must have missed it.
No, just go online.
Okay. If there's no more questions, thanks.